Welcome to the Environmental Science and Engineering Podcast. If you're new here, don't forget to follow and subscribe to stay updated on our episodes, where we explore key environmental challenges, technologies, and innovations from around the world. Today, we're diving into a topic that is both ancient and increasingly relevant in modern times: rainwater harvesting. We'll talk about what it is, how it has evolved, the latest scientific advancements, its implementation across different countries, and the quality concerns surrounding harvested rainwater.
Yes, rainwater harvesting, though rooted in age-old practices, has gained renewed attention in the face of global water scarcity and the growing impacts of climate change. As freshwater resources become increasingly strained, this method of collecting and storing precipitation is once again being recognized as a key element in sustainable water management strategies.
So, what does the current scientific landscape tell us about rainwater harvesting? It seems like this isn't just an old method being reused, it's a rapidly evolving research area as well.
Absolutely. Scientific inquiry is actively shaping the future of rainwater harvesting by improving system efficiency, ensuring water safety, and integrating these systems into modern infrastructure. This includes innovations in collection and filtration technologies, detailed assessments of rainwater quality, environmental impact studies, and hydrological modeling.
Interesting. Has this growing interest been reflected in the academic literature too?
Definitely. According to a search we conducted in the Web of Science database, there are currently 3,857 scientific publications listed under the topic rainwater harvesting. Remarkably, about 50% of these were published after 2019 and nearly 80% since 2010. This highlights how rapidly the topic has gained momentum over the last decade.
And which countries are leading the charge?
The United States and India are at the top, each with nearly 500 publications. China follows closely with over 450. Countries like the United Kingdom, Germany, Australia, Brazil, and Bangladesh also have more than 100 studies each. What's notable here is that many of these countries are either already experiencing high water stress or are proactively investing in sustainable water strategies. Interestingly, Turkey has 51 publications on the topic, showing a growing academic interest as well.
That's quite telling. It seems that rainwater harvesting is no longer just a local or regional practice. It has become a truly global scientific focus, especially in the last 10 years. Let's talk now about how technology is transforming rainwater harvesting. We're no longer just talking about a simple barrel under a downspout, right?
Exactly. We're now in the era of smart rainwater harvesting systems. These are high-tech setups equipped with sensors, Internet of Things, and artificial intelligence. These systems can monitor real-time data such as weather conditions, water levels, and consumption patterns to optimize both collection and distribution.
So they're not just collecting rainwater, but actually making decisions in a way.
Precisely. In urban areas where water demand is high, these smart systems can even anticipate heavy rainfall by discharging water in advance to prevent overflow and reduce flood risk. Some systems also help manage organic matter in the storage tanks, indirectly lowering methane emissions. So they not only improve water efficiency, but also contribute to the sustainability of urban water management.
And I believe these innovations aren't just limited to tanks and pipes. We're also seeing them integrated into urban infrastructure, right?
Yes, very much so. Green infrastructure is a big part of this. For instance, green roofs and permeable pavements are being widely adopted to enhance rainwater management. Green roofs are covered with vegetation and can retain rainwater, reduce runoff, insulate buildings, and even support urban biodiversity by creating habitats for insects and birds.
That's fascinating. So it's both a water and energy solution.
Exactly. Permeable pavements also play a crucial role. Made from porous materials, they allow rainwater to seep into the ground, recharging groundwater and minimizing surface runoff. This is particularly valuable in cities where conventional stormwater systems are often overwhelmed during heavy rains.
And there's a really interesting case from Amsterdam, right?
Yes, the Smart Blue-Green Roofs project is a prime example. These roofs combine vegetation with a crate-based water storage system underneath. What makes them unique is the integration of smart sensors and valves controlled by a decision support system. The system reads weather forecasts and adjusts water storage accordingly, releasing water before storms and conserving it during droughts. This dynamic control reduces the load on urban sewer systems and helps maintain plant vitality while also enhancing biodiversity and resilience in the face of climate change.
So far, we've talked about smart systems and innovative approaches in rainwater harvesting. But here's something that might surprise people. Rainwater is often assumed to be clean. But is that really the case?
Not quite. While rainwater may seem pure, its quality is far from consistent. In fact, it can be significantly affected by factors such as atmospheric pollution, the design and materials of the collection system, and how the water is stored afterward.
Let's break that down a little. What are the main types of contaminants we're talking about here?
There are three main categories: microbial, chemical, and physical contaminants. Microbial contamination is a big concern. Several studies have found fecal indicators in stored rainwater, and even human pathogens like Campylobacter, Cryptosporidium, Giardia, Aeromonas hydrophila, and Legionella.
That's definitely not something you'd expect when you think of rain. What about the chemical side?
Chemical contamination mainly comes from the materials used in the system. For example, rooftops made from asphalt shingles or composite materials can leach heavy metals and other toxic compounds into the water. But it's worth noting that recent studies suggest the levels of these leached substances are generally not problematic for non-potable uses like toilet flushing or irrigation.
Interesting. And physical contaminants?
Those include sediments, debris like leaves and twigs, dust, and even automotive exhaust particles. Organic matter, such as grass clippings, can lower dissolved oxygen levels, which leads to odors and the release of pollutants from sediments in storage tanks.
Okay, so the contaminants are diverse, but how exactly do these pollutants make their way into rainwater?
There are two main mechanisms: wet deposition and dry deposition. Wet deposition occurs when precipitation, like rain, snow, or fog, pulls pollutants from the atmosphere down to the ground. As raindrops fall, they interact with dust, aerosols, and gases like sulfur dioxide or nitrogen oxides, especially in industrial or high-traffic areas. This can result in rainwater with elevated levels of heavy metals, sulfates, or even lower pH values.
So rain can actually be acidic in some places.
Absolutely. In fact, due to atmospheric carbon dioxide, rainwater naturally has a slightly acidic pH. But in industrial regions, this acidity can intensify due to elevated concentrations of sulfur and nitrogen oxides.
And dry deposition.
That happens before it rains. Dust, soot, leaves, and other pollutants settle on rooftop surfaces due to gravity or wind. Then when the first rain comes, it washes all those contaminants into the storage tank. The longer the dry period before rainfall, the more material accumulates, and the more polluted the first flush becomes.
Which means both air quality and what's sitting on your rooftop before it rains can heavily influence rainwater quality.
Exactly. Factors like urban traffic, proximity to industrial zones, roofing material, regional geography, and how long it's been since the last rain all play a role. That's why any serious rainwater harvesting setup must account for both wet and dry deposition to ensure safe use, especially if the water will be reused even for non-potable purposes.
Up to this point, we've talked about the potential risks to rainwater quality. Now let's turn to the solutions. How do we treat and purify harvested rainwater to ensure it's safe and usable?
That's an essential question. While rainwater can serve many purposes, especially non-potable ones, it still needs to be treated carefully. The purification process involves multiple stages, and relying solely on simple, do-it-yourself filtration setups is generally not adequate, especially when high-quality water is needed.
So, what are the first steps in this process?
It all begins with pretreatment. One of the most important components is a first flush diverter. These devices redirect the initial runoff from the roof, the part most likely to carry dust, leaves, animal droppings, and other contaminants, away from the main storage tank. Essentially, it prevents the dirtiest portion of rain from ever entering the system.
That sounds like a smart way to minimize pollution right from the start. Are there other barriers used in this early stage?
Yes, gutter screens and similar screening mechanisms are placed at roof edges and downspouts. They physically block leaves, twigs, insects, and even small animals from entering the system. This reduces the frequency of maintenance and also protects downstream components like pumps and filters from clogging.
And once the water enters the storage tank,
Next comes sedimentation. It's a passive process, just letting the water sit so that heavier particles can settle at the bottom. While it helps improve clarity, it's not enough on its own. That's why we move on to more refined filtration methods.
like cartridge filters?
Exactly. Cartridge filters are often arranged in a series, starting with coarse filters like 20 microns and followed by finer ones down to 5 microns or even lower. This step removes particles that sedimentation cannot.
What about sand filters and carbon filters? I've heard they're commonly used.
Yes, sand filters are excellent for removing physical impurities and suspended solids. After that, activated carbon filters, sometimes called charcoal filters, play a key role. They remove chemical contaminants, odors, and even microorganisms. These filters are especially useful in removing chlorine taste and smell, which may result from disinfection treatments.
Let's move into the more advanced technologies. Where does membrane filtration play into play?
Membrane filtration technologies are highly effective and increasingly common. Reverse osmosis, for example, uses a semi-permeable membrane to remove a wide range of contaminants, from dissolved salts and minerals to bacteria and viruses. It's widely used in industrial applications as well, like recycling water in cooling towers.
Are there other membrane-based techniques being explored?
Absolutely. Nanofiltration is particularly promising. It can target both microbial and chemical contaminants and is being studied for its feasibility in rural or resource-limited areas as a low-cost, sustainable solution. Then there's ultrafiltration and microfiltration, both of which offer reliable physical barriers to remove suspended solids, bacteria, and some viruses.
So, depending on the intended use and local context, a combination of these technologies might be selected.
Exactly. There's no one-size-fits-all. The system design should reflect the end use, whether for irrigation, flushing toilets, or even drinking water, and take into account the local climate, pollution levels, and available infrastructure.
We've talked about membrane filtration in general, but I know that recently there's been growing interest in newer types of membrane systems, especially ones that address energy consumption and fouling issues. Could you elaborate on that?
Absolutely. One of the most promising developments in this area is the gravity-driven membrane, or GDM system. Traditional membrane systems typically require pressurized pumps to operate, which can be both energy-intensive and expensive. GDM systems, on the other hand, use only gravity to drive the filtration process, meaning no pumps, no pressure, and significantly reduced energy consumption.
That sounds like a game changer. But what about membrane fouling? That's always been one of the biggest challenges, right?
Yes, exactly. Fouling, especially biofouling, is a major concern with membrane technologies. However, GDM systems have shown some resilience against this issue. While fouling still occurs, the rate tends to be slower, and the systems are more stable over long-term operation without needing constant cleaning. This makes them especially suitable for decentralized applications or rural settings.
So, how does the water quality from membrane systems compare to other treatment methods?
That's actually one of the strongest points in favor of membrane technology. The treated water quality is often very high, especially when compared to conventional filtration or sedimentation systems. For non-potable uses, like irrigation or toilet flushing, ultrafiltration is usually sufficient. Ultrafiltration membranes can remove most bacteria, viruses, and suspended solids, often achieving removal rates over 99%.
And for more sensitive applications like drinking water or industrial reuse?
In those cases, nanofiltration or reverse osmosis is the preferred choice. These membranes offer even finer filtration, removing dissolved salts, heavy metals, and other chemical contaminants. So if the goal is to produce high-purity water, for example for industrial process use or potable purposes, then using nanofiltration or reverse osmosis is definitely the more appropriate strategy.
So it's really about choosing the right technology based on the end use.
Exactly. Each membrane type has its strengths and limitations, and understanding the application context, as well as the local water quality and economic feasibility, is crucial for effective system design.
We also have a detailed podcast episode on membrane filtration available on our channel. Don't forget to listen. So we've walked through pretreatment and filtration in rainwater harvesting systems, but filtration alone doesn't fully guarantee that the water is safe, especially if it's going to be used for potable purposes. What disinfection steps are commonly used to ensure microbiological safety?
You're absolutely right. Even after filtration, disinfection is critical, especially for eliminating any remaining pathogens. One widely used method is ultraviolet purification. It's a chemical-free technique that uses UV light to inactivate bacteria, viruses, and other harmful microorganisms in the water.
UV seems like a great solution, but are there limitations?
Yes, and it's important to recognize them. If the water isn't adequately pre-filtered, suspended solids can block the UV rays, creating what we call a shadowing effect. This prevents UV light from reaching all of the microorganisms. Some studies have also shown that even when UV is effective, there's a risk of recontamination in the distribution system if it's not properly maintained.
Interesting. What about chemical disinfection methods?
Chlorination is probably the most common chemical method. A specific amount of chlorine, often in the form of household bleach, is added to kill microorganisms. It's reliable and widely used, especially in emergency situations. Of course, some people don't like the residual chlorine smell and taste, so an activated carbon filter can be used afterwards to remove those.
And for those looking for simpler or more accessible options, especially in off-grid areas?
Boiling is an effective option. Bringing water to a rolling boil for at least 5 minutes will kill most harmful organisms. It's simple, but energy-intensive. Another low-tech method is solar disinfection, or SODIS. It uses sunlight to kill pathogens, typically by filling transparent PET bottles and exposing them to the sun for several hours. It's particularly promising in developing regions, and current research is exploring how to make it more reliable, especially against more resilient contaminants.
So it sounds like no single method is foolproof. Would you say integrated or multi-stage systems are the way forward?
Exactly. Many studies show that combining methods, for example, filtration followed by UV or chlorination, achieves far better results than any single method on its own. This is especially important in regions with limited infrastructure where water quality can be highly variable. A multi-barrier approach ensures that even if one layer fails, the others provide a backup.
So the goal is not just clean water, but safe, reliable, and sustainable water through well-designed treatment chains.
Yes, as rainwater harvesting becomes more critical globally, the focus is shifting toward cost-effective, adaptable, and robust systems that work even under constrained resources. It's a growing area of research with big implications for water security worldwide.
Now that we've explored purification methods and system design, let's talk about one of the most compelling reasons for adopting rainwater harvesting: its environmental benefits. Because beyond just water savings, these systems offer real, measurable gains for ecosystems and climate resilience, right?
Absolutely. One of the most significant benefits is the reduction in energy use and carbon emissions. Every liter of harvested rainwater used locally means one less liter needs to be pumped, treated, and transported through a centralized system. This is especially relevant in countries like Germany, where the sewer infrastructure manages billions of cubic meters of water annually. So even small-scale adoption can lead to considerable energy savings and lower emissions.
And I imagine urban runoff is another major factor, especially in cities with lots of sealed surfaces.
Yes, definitely. In dense urban areas, up to 90% of rainfall becomes runoff because of impermeable surfaces like asphalt and concrete. This runoff can overwhelm drainage systems, leading to problems like sewage overflows, chemical contamination, and even stream bank erosion. Harvesting rainwater at the source reduces this burden, acting as a flood mitigation tool and supporting urban climate resilience.
So it's not just about collecting water, it's about protecting the whole urban environment.
Exactly. And beyond cities, rainwater harvesting contributes to groundwater replenishment when it's used for irrigation or directed into recharge wells. Instead of letting all the rainwater flow away, these systems help restore the natural infiltration step of the water cycle, which is essential in areas struggling with aquifer depletion.
And what about soil and plant health? I've heard that rainwater is actually better for gardens compared to tap water.
And that's true. Unlike municipal water, rainwater is naturally free of chlorine, fluoride, and dissolved salts. These additives, while necessary for drinking water safety, can gradually affect soil chemistry and plant health. Rainwater has a balanced pH and promotes healthier root systems and nutrient uptake, especially for sensitive crops.
So, in summary, rainwater harvesting reduces our carbon footprint, helps prevent floods, supports groundwater recharge, promotes healthier ecosystems, and even reduces strain on existing water supply systems. Quite a list.
And with increasing global water stress, all of these benefits become even more critical. Rainwater harvesting isn't just a sustainability trend. It's becoming a foundational strategy for future water management.
We've seen how rainwater harvesting brings environmental benefits and how it can be effectively treated and reused. But how do different countries regulate and promote this practice? The legal and policy landscape seems to vary quite a bit, doesn't it?
Yes, it does. Let's begin with the United States. While rainwater harvesting is generally legal at the federal level, water laws are primarily handled by individual states, so there's a wide variety of approaches. For instance, Colorado, which once had some of the strictest laws, now allows residential collection with a 110-gallon limit. Nevada and Utah also have specific restrictions on storage capacity and use, especially for non-potable purposes. On the other hand, states like Washington and Oregon are more permissive, provided certain design and safety standards are met.
That level of decentralization must make it tricky for scaling up systems. How about the UK?
In the United Kingdom, rainwater harvesting is not illegal and generally doesn't require planning permission except for special buildings like heritage sites. However, their building regulations are very strict when it comes to separating potable and non-potable water systems. Pipework must be clearly labeled and air gaps are required to prevent any cross-contamination.
What about countries that are known for environmental leadership, like Germany?
Germany is a global leader in rainwater harvesting, with over 1.8 million systems in use. What's impressive is their policy integration. Rainwater fees are separated from wastewater fees, creating financial incentives for households that infiltrate rainwater or reuse it. Subsidies and tax breaks up to €12,000 per household also support system installation. Municipalities even incorporate rainwater harvesting into stormwater management strategies.
That's quite advanced. Are there similar initiatives in Asia or Latin America?
Definitely. Japan, for example, passed the Rainwater Act in 2014 and mandates RWH in government buildings. Local governments like Tokyo's Sumida Ward even support citizen-led innovations like the Rojisan system. In Brazil, the Cisterns program has installed over 1 million rainwater tanks in semi-arid regions, helping vulnerable rural populations, especially women, access clean water for drinking and agriculture.
So even developing countries are integrating RWH into long-term strategies.
Yes, very much so. Sri Lanka, Uganda, Thailand, and Bolivia all have community-level or school-based systems. Bermuda takes it even further. It legally requires RWH in all new buildings. The global shift is clear. We're moving from cautious adoption to active encouragement and standardization.
That said, it sounds like some challenges remain, especially around consistent guidelines and public health protections.
Exactly. While RWH is increasingly recognized as a valuable tool for climate adaptation and sustainability, there's still a critical need for harmonized regulations, especially around system design, water quality, and contamination risks. Successful implementation depends on a careful balance between local context and scientific.
That wraps up our deep dive into rainwater harvesting. In this episode, we explored what rainwater harvesting is, the latest scientific advancements, water quality concerns, purification methods, environmental benefits, and global regulations and case studies.
Exactly. We cover both the technical aspects and practical implementations, showing how this ancient practice has evolved into a modern solution for water sustainability, especially in the face of climate change and water scarcity.
If you enjoyed this episode and want to keep learning about water, sustainability, and environmental engineering, don't forget to subscribe and like the podcast. Your support helps us reach more people and continue producing evidence-based content.
And if you have thoughts on how we can improve rainwater harvesting or experiences from your own country, feel free to share them with us. We'd love to hear from you.
You can find us on YouTube, Spotify, and Instagram under our podcast name. All of our content is created by environmental engineers and researchers based on peer-reviewed papers, official reports, and global best practices.
So don't forget to follow us, share the episodes with your network, and stay connected. See you in the next episode.
Take care and stay sustainable.